Okay, in this video I'm going to talk about Boyles Law. Boyles Law is the relationship between pressure and volume. First of all, we should note the assumptions here. Here we're assuming that the temperature is constant. And that the number of gas molecules is constant. So what we're really focused on here is when I change the pressure, how does that change the volume? Or when I change the volume, how does that change the pressure? Recall what we talked about, excuse me, that pressure is the force delivered per unit area by these gas molecules colliding. So if there's a small balloon versus a large balloon and the same number of gas molecules banging into the side in either situation, then the area that those gas molecules will be banging into will be much larger with the larger balloon. What that means then is if the area is larger, the area goes up. Since it's in the denominator, that means that the pressure will go down. So as volume increases, pressure decreases. Mathematically, we call this an inverse relationship. And this is just a straight inverse relationship here, where volume is inversely proportional to pressure. Or I could say pressure is inversely proportional to volume. To look at changes in pressure, if I want to say compare pressure 1 to pressure 2 or volume 1 to volume 2, I can create ratios using these. If I say that pressure 1 is equal to something, or if I want to see how the pressure in situation 1 compares to pressure in situation 2, because this is an inverse relationship, I put the volume associated with the initial situation inverse to the original pressure. Similarly, if this pressure is on the bottom, I put the volume up here when creating a ratio. This ratio can also be written P1 V1 is equal to P2 V2 by bringing the denominators up to the other side. An application of this, one that I particularly like, is the suction cup. Here, I'm going to try and draw this. We can imagine a cup like this, where there's a certain volume of air underneath it. And then we can imagine squishing that cup, pushing on it to squish it, and pushing the air out, and then creating a seal where the volume within this area is greatly reduced. The suction cup will try to go back to its original shape. The suction cup will attempt to come off of the wall. This is the wall. But inside this, as long as the gas molecules have been pushed out and have been sealed, as this volume tries to increase, the pressure inside this little sealed area will decrease. As volume goes up, pressure goes down. Now if we imagine the force being exerted by the air molecules in and outside the suction cup here in this area with low pressure, there are not very many gas molecules available to deliver force to the inner surface of this suction cup. So there is a very small push in this direction. Alternatively, the air pressure outside the suction cup is still delivering the large amount of force associated with the atmospheric pressure. So there's a large push in this direction. This large push keeps the suction cup stuck to the wall. This one wins, and so the suction cup sticks. Example, a balloon is placed in a sealed container. The initial volume of the balloon is 2.6 liters. The initial air pressure of the container is 100 kilopascals. The gas surrounding the balloon is then pumped out of the container, reducing the pressure to 20 kilopascals. What is the final volume? Yep, that should be a question mark. So here's a numerical example that will illustrate how we can use Boyle's Law mathematically. So again, we have our initial volume. So that's the size of our balloon before we start pumping air out of this bell jar container. Our initial pressure, 100 kilopascals. We're going to pump air out until the pressure goes down to 20 kilopascals. And we're going to see what happens to the balloon. So let's just be clear. Let's imagine this is our container, and we have our little balloon in it. And usually there's a whole bunch of air in here, and this air is flying around and banging into stuff, and one of the things it's doing is banging into the side of this balloon, and the balloon has air in it, and the balloon is pushing back, and those two, the particles that are hitting the outside of the balloon and the particles that are hitting the inside of the balloon, are of equal strength. They're pushing against each other, and so nobody's winning, and that's why the balloon has its fixed volume. Now we imagine we attach some sort of pump where we can take these gas molecules and pull them out. And what that means is the pressure in here will decrease, and less gas molecules will be hitting the outside of this balloon. So the guys pushing inside haven't lost any strength, but the guys pushing on the outside have lost strength. And what will happen then is that the balloon will get larger and larger and larger until the particles hitting from the inside and the particles hitting from the outside have the same strength as each other. So we expect this volume to increase. I find when I set up these ratios, it makes my life a little easier if I put the unknown thing on the top on the left-hand side, so it's already solved. So V2 over V1, and then because it's an inverse relationship, it's going to be P1, see it's on the bottom, so it goes to the top. See it's on the top, it goes to the bottom, P2. And I get this inverse relationship. So V2 over 2.6 liters is equal to P1, 100 kilopascals, over 20 kilopascals. So V2 would be equal to 2.6 liters, and this 100 divided by 20 is just 5. And then multiplying both sides by 2.6, I get a V2 of 13 liters. So this balloon, we dropped the atmospheric pressure way down, but what happened was then this balloon expanded and expanded and expanded to fill the space that that gas used to exist in. So that is a numerical example of Boyle's Law. So once again, because pressure is force per unit area, if we increase the area, then effectively we're decreasing the pressure. If we one example, this is the suction cup, where by this attempted expansion or going back to its original shape, the suction cup reduces the pressure inside of it. Since the pressure outside is still high and the pressure inside is low, the pressure outside wins and sticks the suction cup to the wall. And this is how we can handle Boyle's Law numerically.